equation of the regression line. And this is our equation here, which is y prime equals a plus b times x, where the value of a is found with this calculation here, and that's considered the y prime intercept, and the value of b, which is the slope of the line, is with this calculation here. So we have some familiarity with utilizing a formula in the previous section, which was a correlation value, and more or less the information that we need to calculate the value of a and b is the same. Everything that was in that formula is presented here in finding the value of a and the value of b, with the exception we're not taking the square root of anything. But we're not actually going to carry out the formula because of how time consuming it was previously. I'm just going to show you how to find the values and how to interpret those values. Mainly with this formula, if you are familiar with linear functions, it is somewhat of the form y equals mx plus b. And so this is the equation of a linear function in slope-intercept form, where the value of m is the slope because it represents the movement of the graph. And in our formula here, the value of b is our slope. And in our slope-intercept form equation, this is the y-intercept, which is simply the location where the line crosses the y-axis. But in our regression line formula, this is the y-intercept, or the y-prime intercept. In this equation, the value of y, this would be for a perfect linear relationship, if the correlation value is 1. When we don't have a perfect linear relationship, we look at a regression line. We are estimating the relationship and the trend by finding these two values for the y prime intercept and the slope. Y prime is considered a predicted value, and I'll talk more about that when we look at some of the data. But our y prime is considered a predicted value because that's what we are predicting. So I want to actually use the same two examples that we talked about previously, because we've already talked about their correlation. We found their correlation value, so then we can talk about how accurate the trend line is based on that correlation. So similar, the same data as before with the gestation and the longevity, and we even have the same question: is there a linear relationship between the gestation of a sample of animals and the average longevity? And we want to write and interpret a regression equation. So more or less, we would like to find y prime equals a plus b times x, and we want to predict the value of y prime when the value of x is 200. So there's two things we want to do here. We want to calculate the regression equation, and we want to interpret the regression equation. What is it? What do the components mean? And then when we're finished, when the number of days for gestation is 200, then what is the predicted longevity? That's what we would like to determine. So to find the regression equation, I'm actually going to show you how to do that. Instead of using the formula, we know how long that took in the previous section. I'm going to go straight and show you how to find the information we need from using the calculator, because you only need to be able to find the numbers and then use those numbers to get the equation and then interpret the values. So I've already entered the data again into the list. So just to reiterate that process, we always are going to use the statistics button, so stat, and then we're going to edit, and we have to type our data into the first list and the second list. So the first list represents the days of gestation, and the second list represents the longevity in years. So this is our X, this is our Y. And I want to go back to stat, and I want to calculate. And the very same thing that we did before was linear regression. so we can get the R value, and I'm going to go back to linear regression so we can get the values of A and B. Now, let me go ahead and do that first. We don't have to change the list labeling unless we typed our data into a different list. So if I didn't put the X values into the first list, then I would have to change it using the blue options here. So this is list 4, list 5, list 6, and so on. Just use second in that, but we keep it as list 1. And I want to go down to calculate. Now, it gives me the R value again like we found earlier, and earlier I kind of ignored the value of A and B. Now, there is a difference here because this linear regression equation is not, well, these values of A and B are not that values of A and B that I'm going to use. I have to switch them around. The equation that I would like to write is y prime equals A plus B times X. So if I compare the two equations, this is the y-intercept, this is the y prime intercept. It's the value that does not contain the variable. It's the value that is not associated with the variable. When this variable is equal to 0, so when this equals 0, then that A value is the location of where the graph crosses the y-axis. If I look at this equation over here, well, that's this value. So in your calculator, it's programmed to use the values in a different way. So, and I mention it this way because the equation, the linear regression equation, is actually built in the calculator around slope-intercept form, y equals mx plus b. But for us in this course, we have our linear regression equation is not built around that per se. We want to look at the values as y equals a, where a is our y-intercept or our y prime intercept, and that actually is the b value here. Because in this setup, the b is the y-intercept. It's the value without the variable x. And this is the slope. So my slope is always the value, that's the coefficient or the number being multiplied by x. So that in this case is the value of a. The slope is the rate of change, and it's related to the value of x in that way. So in my linear regression equation for y prime, b is the slope. That's not this b, because in this setup here, a is the value being multiplied by x, or the coefficient of x, so this is actually my slope. So if I were to write out my equation using these numbers, it would be y prime is equal to negative 2.95, that's the y-intercept, plus 0.106x. So that would be this would be my regression equation that we would use, or that we would need in order to go ahead and make some predictions with that information. So I'll do another one again in the next example. But this is the information that I need to perform my predictions. So copy. There we go. Just wanted to, there we go. So this is my regression equation. Now that's the writing part. We also want to be able to interpret this equation. So what does this equation mean? So y prime, this is the predicted longevity. So this is our predicted longevity. And it retains the same units as the original data. So the predicted longevity in years. The value of x is more or less, this is still gestation. We're not really predicting the gestation because we're going to be given that information. So this is still just gestation. And for this one, it's in days, because that's what the problem told us. Now, this value, which is the y-intercept, it may or may not make sense for the situation, right? So the y-intercept is more or less like a starting value. So if the gestation period is 0 days, then we expect the animal to live negative 2.95 years. That really doesn't make any sense, right? But that's literally what it means in this situation. So this is when the x value, this is the y prime intercept, when the x is equal to 0. It's just a location where it crosses the x-axis. So in this particular problem, it doesn't really have a real meaningful meaning. The meaning is not meaningful because it doesn't make sense that if the gestation is no days, then it's going to live negative 2.95 years. And when we look at the graph of this, I'll tell you why. I'll be able to visually show you why it doesn't really make sense. And then the slope, this is the average increase. This is the average increase in longevity for every per day. So this is the average increase in the longevity of years per day. So it's like 0.106 years per day. So average increase in longevity for each day of gestation. So that's more or less kind of our interpretation of that entire equation. More or less for us, we're mainly just concerned with, our prediction here. And then we talk about how great is that prediction. So when we found the R value, we determined that these two quantities were correlated at 0.57, I believe, 1. So it really wasn't a strong correlation. So your prediction is as strong or is as accurate as your correlation value. So this was just these are moderately related. So our prediction is not really going to be that great. However, we can still make a prediction. And what we would like to do, and I wrote this down earlier, it tells us predict the y prime value. So this is like a question mark when we know that they are 200 days gestation. So one thing we want to ensure that the value we're using is within the current data set. So I can use 200 because it lies between the smallest number in my data set and the largest number. I wouldn't be able to predict the gestation for 10 days because I don't have data to support that. I wouldn't be able to predict the gestation for 1,000 days because I don't have data to support that. This equation is only based on these 5 pairs of data with the least number of gestation days with 105 and the greatest at 285. So we can use this number to kind of make a little prediction here. And because that's an x value, we can just substitute it in. So y prime equals negative 2.95 plus 0.106 times 200. And that's my x value. And we just substitute in that value. And then we just perform the operation. So for that, you could easily use your calculator to do that. Negative 2.95. Negative. Don't use minus, because then, like it did for me, it will try to take whatever you previously typed in, and that's not going to work. So we're going to use negative 2.95 plus 0.106, I believe. Yep, times 200. Times 200. So 18.25 years. So it's predicting y prime 18.25 years. And then if I were to summarize that, for an animal that gestates, so for an animal that gestates for 200 days, we predict its offspring will have a life expectancy of 18.25 years. And I wanted to go back to the graph here. So when I look at the this dotted line is the regression line that we found in the calculator. So the equation for this line here is y prime equals negative 2.95 plus 1.06x. And mainly the line doesn't continue in both directions because it's only valid for the data that we have on the graph. So it starts at around here and stops at this point. And if I look at 200, so we were predicting this value, and if I look at my line, this is the 18.25 that we got. So that's a prediction. Any point on this line is just a predicted value. That's what the y prime indicates, that these are all the predicted longevity values based on the 5 points that we have access to. If we were to extend this line this direction, so if I were to actually extend that line out, yeah, I didn't do a very good job doing that, but hold on. If I were to extend it, that's why the y-intercept is negative. That's why this 2.95 is negative, because the value will cross the y-axis below 0. So when we look at when we're trying to analyze data, I really can't guarantee that this is the trend. For one, no creature is going to live negative 2.95 years. But in reality, the data that I'm basing my prediction off on is only these 5 points. So if we had access to, I don't know the lifespan for any animal less than 100 days, and I don't know the lifespan for any animal greater than this point, this many days. So if we had access to more information, we can make we can have a better prediction. Our prediction is also not really that great because of this value. These points, this value here is throwing off our correlation, so it also is going to throw off our prediction because this equation is based on this value and it has a much higher lifespan than other points relative to it. So those are things we want to consider. So we'll look at another example. Same with the crime statistics we looked at with the murders and the robberies. Now this had a moderately high correlation. It was 0.801, I believe. And so we can certainly we can get a better prediction out of this one because of the correlation value is much higher. So for that problem, the second problem, I went ahead and typed the information in the table like I did before, so I don't have to show you that process again. But to get to the table, we go to Stat, and then we want to go to Edit. So number 1, enter in the data in the table. List 1 is X, list 2 is Y. Go back to Stat, and then go over to Calculate. And then we're still doing number 4, which is linear regression. So number 4, and I want to go down to linear regression and calculate. And it gives us our R value, moderately strong, 0.804. So we know that when we do our regression equation, we're going to get a little better prediction than we did previously. And so we have to kind of remember here that I talked about earlier that in my equation that I would like to write, y prime equals a plus b to the x. So we have to consider that the a that we want is the y-intercept, and that's actually this number here. This is the y prime intercept from this output. So negative 13.15, and then the value of b that I want is the slope, which represents this value here. So 25.33. And this will be my equation that we're going to use. We're going to break down the equation, and then we're going to use the equation to make a prediction. So copy. So just like before, we talked about what each component meant for the equation. X are the murders, Y are the robberies. So our Y prime, this is predicting the robberies. So anything that this equation is going to give us is predicting the number of robberies. Predicting number of robberies. And our X represents the murders. So this is the number of murders. Now our y-intercept is always the same meaning. When there are no murders, we expect negative 13.15 robberies per 100,000 people. And again, that doesn't make sense because of how the data is. So we really, this value rarely makes sense in situations. So this is just the value when x equals 0. So when there are no murders, we expect negative 13.15 robberies per 100,000 people. So that rarely makes sense for certain situations. Now the slope is something that we can interpret pretty easily because it's based on the average change in the data. In this case, we're looking at the number of murders and the number of robberies. So we expect, this is an average increase, so average increase of 25.33 robberies per murder, pretty much, per murder. And again, all of these values are in per 100,000 population. And then now that we know that information, so every time our murders increase on average by 1, this is the number of robberies that we expect. So now we can use this to make a prediction, or we can find the value of x. So again, we want to, it says write and interpret the regression equation. So we wrote it. This is our interpretation of each of the components. And I want to predict y prime. So I want to predict the number of robberies when there's 4.5 murders. So I go over to my list. 4.5 is definitely within the data set. The least number of murders per 100,000 people was 2.1. And the greatest number of murders per 100,000 people was 6.6. 6.6. So that value is definitely within that data set. And so now I can use this equation to predict the number of murders, or to predict the number of robberies. So if I take my y prime, and that's equal to negative 13.15 plus 25.33, and the value of x is 4.5, this is what I want to figure out what this value is. So I go back, and that's just a calculation that I'm going to perform. So negative 13.15 plus 25.33 times 4.5. So we're predicting that we have 100, about 101. Pull back up my writing. We're predicting about 101 robberies for those 4.5 murders. So 101 robberies, about. And I can confirm this by looking at my graph, because I did make a graph earlier, or I'm using the same graph that I had shown earlier. So if I go to 4.5 murders, which is about here, then if I look at my line, my trend line, it's about 100. It's a little bit above 100. It's about 101. So any point on this line represents a prediction based on the current data. And then some of the points, so any point that is above the line underpredicts for that point. So like this point here, if I go down to the x-axis, whatever that value was, let's say 2.7. At 2.7 murders, it's predicting, the line is predicting this many robberies. So this is the predicted. However, this is the actual. And so that difference between the actual and the predicted is called a residual. It's like an error estimation. In this case, the line, the prediction line, the regression line is under predicting in that instance. And then for this one over here, so for this point at, I probably could go back to the table, but I don't want to stretch it out. Let's say 5.8. This is the actual, and the line is predicting this much. That's the predicted. Well, the difference between those is called a residual, and in this instance, the line is over-predicting. So throughout the data set, there are points that are being under-predicted, and there are points that are being over-predicted. And what's happening is through the regression process, we are trying our best to estimate, based on the relationship between the points, a trend line, a perfect fit, which we really don't have a perfect fit because of this value. The closer this is to 1, the more these points are going to be clustered towards that line. But for us, we just have to be able to find the equation and then use that equation to make some predictions.